You know, when you look at a skyscraper, what do you really see? Just a building, right? A static structure of steel and glass? But what if it could be more than that? What if our buildings weren't just shelters, but were actually alive?
I mean, let's be honest. Right now, our buildings are pretty much dead. They're just lifeless shells. And that simple fact, it turns out, is causing some massive problems for our cities.
So on the left, you've got our current reality, these static shells that just soak up the sun and radiate heat back out at us. But on the right, well, that's a completely different vision. It's a living organ that actually filters the air, breathes in CO2, and even generates its own energy. This is the whole idea behind a new technology called Aero-Vascular Algae Cladding, or AVAC for short.
Okay, so why is this such a big deal? What are the real consequences of wrapping our cities in what the source material calls dead skin?
Well, it creates this really nasty feedback loop. Our buildings literally bake our cities. That's the urban heat island effect you always hear about. They're also totally passive, just sitting there, missing huge opportunities to capture free energy from the wind and the sun. And it all adds up to more carbon emissions, worse air quality, and cities that just keep getting hotter.
But what if we could completely flip that script? What if our buildings could stop being the problem and actually become part of the solution? This gets us to the really exciting part, the vision of a building that can actually breathe.
This quote just nails the whole concept. We have to stop thinking of a building's outer layer as just some passive armor against the elements, and start designing it to be an active, metabolic skin.
And here is the technology that could make that a reality. AVAC. It sounds really complex, but it's basically a mashup of three key technologies: harvesting wind energy, using tiny microfluidic channels for circulation, and filling those channels with algae. You put it all together, and you literally transform a static box into an active, living organism.
So, how on earth does this actually work? Well, you build it one piece at a time. Think of it like a single cell.
The basic building block of the whole AVAC system is this thing called a biotile. It's a modular panel, and inside each one, you've got a tiny wind harvester, an even tinier pump, a capillary mat for the algae to live in, and some smart sensors to keep an eye on the whole operation.
Okay, so first things first, where does the power come from? The wind. You can think of the wind as the constant heartbeat that keeps this entire living system alive.
And it gets that power in a really clever way. It uses something called aeroelastic flutter. Now, this is a phenomenon that engineers usually try to avoid at all costs. It's the same kind of vibration that famously ripped the Tacoma Narrows Bridge apart, but here, they've actually harnessed that destructive force. A special ribbon flutters in even a light breeze, creating this constant vibration.
That little ribbon is made from a piezoelectric material, which is just a fancy way of saying it generates an electrical charge whenever it moves or vibrates. So you get electricity with no turbines, no gears, just simple motion turned into power. And that tiny bit of electricity is what powers the building's circulatory system, its veins.
Now, this part is really cool. The pump has zero moving parts. None. It uses the electricity from the vibration to create pressure, and then a tiny crescent-shaped obstacle inside the channel makes sure the fluid can only flow in one direction. It's basically a one-way valve for liquid, which makes it incredibly reliable and perfect for a system like this.
So we have a heartbeat from the wind, and we have veins powered by that vibration. But what exactly are they circulating? Well, the building's lifeblood, living microalgae.
The real star of the show is a specific type of algae called Chlorella vulgaris. This stuff is amazing. It's incredibly hardy, grows super fast, and it is an absolute beast at photosynthesis, literally scrubbing CO2 right out of the city air. The algae and water also help regulate the building's temperature. And get this, the constant circulation creates a flashing light effect, which actually makes its photosynthesis even more efficient.
So just how efficient is it? Well, a single square foot of this living skin can sequester about 5 grams of carbon dioxide every single day.
And to put that into perspective, check this out. A 10,000 square foot facade, the side of a pretty decent-sized building, would have the CO2 capturing power of roughly 800 mature trees. Just let that sink in for a second. An entire forest wrapped around a skyscraper.
A system powered by the winds sounds fantastic, but of course, it has a potential vulnerability. So let's take a look at how this system handles its biggest challenge. This is the critical question, isn't it? What keeps the whole system from failing on a hot, dead calm summer day?
Because without a good backup plan, you get what the designers call the dead zone. No wind means no power, which means no pumping. The algae just sits there stagnant, essentially cooking in the sun, which leads to a total collapse of the biological culture. Game over.
So obviously they planned for this. The system has built-in redundancy, just like a real biological organism. Each tile has a supercapacitor that stores up energy, allowing it to pulse the pumps during calm periods to keep things moving. If that fails, a low-power grid backup kicks in. And in a real emergency, like a heat wave, a thermal dump valve can drain the hot algae into a cool holding tank to save it.
All right, so with that fail-safe system in place, let's zoom out and really imagine what this could all mean for the future of our cities.
This table really says it all. I mean, compared to standard glass, it's a massive upgrade. But even when you compare it to older algae facade designs, AVAC is a complete game changer. Its energy source is on-site and totally free. Its operational cost is near zero. And because it's solid state, maintenance is way lower.
And the result, the ultimate vision, is a city that's actively restorative. A city where the buildings themselves are cleaning the air, cooling the streets, and creating a living, breathing architecture.
It's an absolutely incredible vision. And it leaves us with one last big thought. If we can make our buildings come alive, what else can we reimagine? The big takeaway here isn't just about one specific technology. It's about a massive shift in thinking. The future of our cities could be one where our architecture isn't just a part of the environment, but a living, breathing part of the solution.
Let's be honest, our buildings are kind of dead. They're just concrete, glass, and steel. They take resources, they consume energy, and they don't really give much back. But what if they could come alive? Today, we're diving into a really cool concept called Aero-Vascular Algae Cladding, or AVAC for short, and they could totally transform our cities from the outside in.
I want you to just think about this for a second. What if our giant, static skyscrapers could actually breathe? You know? What if they worked less like concrete boxes and more like living things, actively participating in the world around them? It's a pretty wild thought, and it's the exact question that ACV AVAC is trying to answer.
And there is a huge reason we need to be asking this question. Right now, our buildings are a massive part of the climate problem. They're responsible for about a quarter of all energy-related emissions around the world. That is a staggering footprint for something we usually just think of as a place to live or work.
So this brings us to the core mission behind all this research. The goal isn't just to make buildings a little bit greener. No, the idea here is to completely transform these inert, concrete monoliths into living, breathing, metabolic systems. Systems that don't just suck up energy, but actually generate it, clean the air around them, and even manage their own resources.
Okay, so how on earth do you build a living skyscraper? Well, the AVAC concept isn't just one single invention. It's actually a brilliant combination of 3 different but interconnected pillars of research. Let's break them down one by one.
The first pillar is something we can think of as the building's heartbeat. It's all about energy. I mean, even the most solid-looking skyscraper is constantly vibrating, flexing, and moving ever so slightly in the wind. AVAC proposes to capture all of that constant, subtle motion.
So here's how it works. The wind creates these constant, tiny vibrations on a building's outer surface. The AVAC design embeds these special, flexible materials called piezoelectric reeds right into the panels. Now, piezoelectric is just a fancy word that means they create a small electric charge when you bend or squeeze them. So as these reeds flex with the wind, they convert that mechanical stress directly into electricity. The building literally generates its own power just by standing there.
So if the vibrations are the building's heartbeat, then the second pillar has to be its vascular system. Yep, just like the veins in a leaf or in our own bodies, this system is designed to circulate life-sustaining fluids all through the building's skin. But instead of blood, it's circulating microalgae. And these tiny little organisms are absolute powerhouses. Pumping a living culture of microalgae through the facade gives you a whole bunch of benefits all at once. For one, the algae act like a microscopic forest, literally pulling CO2 out of the city air. They also create a natural dynamic shade from the sun, which can lower cooling costs. And as a bonus, the whole system produces valuable biomass that can be harvested and used for other things. The third and final pillar is this idea of the building's exterior as a living skin. And this goes way beyond just being a container for the algae. It's about designing a surface that can intelligently interact with the atmosphere, especially when it comes to one of our most precious resources, water.
And this is achieved through something called biomimicry, which is basically the practice of learning from and mimicking strategies that nature has already perfected. The surface of an AVAC panel is textured with these microgrooves, inspired by things like the Namib desert beetle, which can literally pull moisture right out of the fog, and cacti, which are absolute masters at channeling water. This allows the building to harvest its own water from rain and even from humid air. Incredible, right?
So we have a heartbeat, a vascular system, and a living skin. The absolute genius of AVAC is how it weaves these three amazing ideas together into a single, multi-layered panel. Let's actually see how it's built from the outside in.
Okay, so the very outermost layer is that biomimetic skin we were just talking about. It's a transparent, textured surface, probably made of glass or a tough polymer. This is the layer that faces the weather, and its special texture is engineered to grab every single possible drop of moisture and channel it right into the system.
Then, just inside that skin, embedded along the panel's edges, you've got the piezoelectric reeds. These things are the engine of the entire system. As the wind buffets the building, these reeds start to vibrate, generating the constant, gentle heartbeat of energy that's going to power everything else.
And this next part, this is where it gets really clever. The energy from those vibrating reeds, it powers a super simple, zero-energy pump. Seriously, think of it like squeezing a tube of toothpaste. The vibrations mechanically squeeze these little vascular channels, which pushes the algae mixture through the facade. No external electricity is needed at all. The building's own movement circulates its own lifeblood. It's a completely closed-loop, self-sustaining system.
The final layer is the interior interface. This is where the living skin plugs into the building's central nervous system, so to speak. It allows for thermal exchange, using the circulating algae to help cool the building in the summer, or even provide insulation in the winter. And it's also where all that harvested water and biomass can be collected and managed.
Now let's scale this up. What happens when you go from just one panel to an entire city? When you start to imagine cladding whole skyscrapers in these living systems, well, the potential is just immense. We're not talking about a single green building anymore. We're talking about an entire breathing metropolis.
And the difference becomes crystal clear when you put them side by side. Where a conventional tower just consumes huge amounts of energy, pumps out carbon, and relies completely on the city for water, the AVAC building generates its own power, has a negative carbon footprint because it's absorbing CO2, and it actively harvests its own water. It's a total game changer.
And this isn't just some far-off sci-fi concept, It actually comes with a practical blueprint for how to make it happen. The plan kicks off with R&D and prototyping, then moves to pilot projects on actual buildings to gather data, and from there, the goal is full commercialization within about a decade.
The long-term impacts could fundamentally reshape our urban ecosystems. Widespread use could help fight the urban heat island effect, create a whole new circular bioeconomy based on that harvested biomass, and just make our cities fundamentally more resilient to climate change.
The researchers behind this synthesis put it perfectly. They said AVAC represents a paradigm shift, transforming buildings from passive energy consumers into active, regenerative systems. That really just captures the massive ambition here. It's about changing the very definition of what a building is and what it can do for us.
For centuries, our buildings have just been these static objects that we live inside. AVAC imagines a future where that relationship is a two-way street, where our buildings actually work with us and for the planet. So I'll just leave you with this thought to chew on. What really happens when our cities finally come alive?
Think about the last time you walked past a brand new skyscraper.
Oh, glass and steel, right, monumental.
Exactly, monumental, but also kind of sterile and cold. It feels rigid, like a monument to consumption.
Mm-hmm.
And that really is the core paradox of modern architecture.
Yeah.
Our buildings, well, they shelter us, yes, but they're also just massive energy sinks.
They pump out greenhouse gases and, they actively ignore the local ecosystems all around them. They're just inert.
Passive and incredibly demanding.
And the numbers, they really back that up.
Yeah.
When you look at the global impact, buildings account for roughly 25% of all energy-related emissions.
The quarter of everything.
It's huge. And the conventional carbon capture tech we always talk about, the projections show it'll only mitigate a tiny fraction of that by 2050.
Mm-hmm.
We need something more fundamental.
Something bio-inspired.
A revolution, really.
Exactly. And that is the mission of this deep dive. We're asking, what if a building's facade wasn't just a passive barrier, but a truly living, breathing, regenerative skin?
And that brings us to the concept of Aero-Vascular Algae Cladding.
Or AVAC.
Right, AVIC. It's one of the most exciting living building envelope proposals I've seen. The genius is in the coupling.
The coupling of what exactly?
It takes two things that seem totally unrelated, the constant low-level wind vibrations that are always hitting a building, and a complex peristaltic fluid network circulating microalgae. It forces them to work together.
So it captures CO2, generates energy, and recycles water, all in the facade.
Turning it into a dynamic metabolic system.
It honestly sounds like pure science fiction.
But it's not. It's grounded in three very distinct academic research strands. And today, we're giving you the shortcut to understanding how kinetic energy, microalgae, and biomimicry all converge to make this possible.
Okay, let's unpack that first foundation then. Harvesting the building's heartbeat.
I like that framing.
Every building facade, especially on a high-rise, is constantly moving, right? Flexing, shifting with the wind.
Usually that's just seen as a structural nuisance, but this first study looks at it as a constant source of energy.
And this is the work from Pocucci and his colleagues in 2024.
Yes. And their original focus wasn't even this grand. They were looking at something called structural health monitoring, or SHM.
So just keeping tabs on the building's integrity.
Exactly. They wanted to know if they could embed these thin, flexible piezoelectric elements into the facade panels to harvest enough energy from those vibrations to power some small sensors.
So for anyone who's not familiar, piezoelectricity is it's basically the electric charge that builds up in some materials when you squeeze them.
The spark in a gas lighter is a perfect example.
Right. So in this case, the wind is providing the squeeze.
Precisely. And what they found was revolutionary for SHM. They confirmed that, yes, ambient wind provides a continuous, reliable source of energy.
How much are we talking about?
Milliwatts. It's tiny, but it's enough for a self-sustained sensor network.
So the building can monitor itself without needing miles of wires or someone changing batteries all the time?
Exactly. But the key insight, the real science nugget, isn't just that it works, but where and how.
Okay.
The harvesters have to be placed optimally. They found vibrations are strongest at panel edges and corners. And, this is crucial, they have to be tuned to the natural frequency of the panel itself.
So you have to find the building's resonant sweet spot.
That's a great way to put it. When you match the harvester's resonance to the panel's dominant vibration, the efficiency just spikes.
Okay, now here's the leap. This is where AVAC takes that science and just shifts the whole paradigm.
Right.
Pocucci wanted to power a tiny sensor.
Right.
AVAC says, forget the electricity. We want the movement.
That is the genuine leap. Instead of turning the kinetic energy into electricity to power a motor, AVAC uses the physical motion of those flexing piezoelectric reeds to directly drive the system.
So the vibration of the building is the engine.
Yes. The wind's frequency dictates the pumping rhythm for the algae circulation. It's using the building's own mechanical energy as motive power.
That sounds amazing, but what about a calm day? If the whole system depends on being perfectly tuned to the wind, does it just stop?
That's a great question, and that's where the engineering sophistication comes in. The system actually has mechanisms for frequency adaptation. It can, let's say, store up that mechanical energy and release it in pulses.
Okay.
So even in low wind, you get sufficient circulation. And yes, for an extreme calm, you'd need a small energy buffer, maybe a tiny solar assist, but the vast majority of the power comes directly from the building's skin flexing in the wind.
So we're not just getting a little electrical trickle, we're using the building's constant shimmy as a giant distributed heart pump for a living system.
That's it, exactly.
Okay, shifting gears, let's look at that second foundation. Turning the building into a carbon sponge.
This brings us to the research on building integrated photobioreactors, or PBRs. We've already said buildings are a huge emission source. The goal here is to flip that, to turn the structure from a carbon source into an active carbon sink.
And this is where the microalgae come in. They really are biological superstars, aren't they? It's not just one benefit.
Not at all. It's a whole stack of them. Microalgae, something like Chlorella vulgaris, are incredibly efficient at photosynthesis. Way more than trees.
So they're sequestering CO2. What else?
They produce valuable biomass. You know, organic matter you can harvest and turn into biofuels, biofertilizers, even bioplastics. It drives a whole circular bioeconomy right there on the building.
And it provides shading.
A huge one. That shading, plus the thermal mass of the fluid itself, dramatically cuts down on solar heat gain. That means less air conditioning.
So you get a biological thermal shield that's also producing valuable stuff.
Precisely. Now, the research is very clear that you need to use closed photobioreactors.
Guys, that's so important. Why not just have open algae ponds on the facade?
Control. In a closed system, you get superior environmental control, higher efficiency, and you prevent contamination.
Which would be a huge problem in a city.
A massive problem. With a closed PBR, you can precisely control temperature, nutrients, CO2 injection, everything you need to maximize growth. You get a sterile, highly productive environment that's perfect for modular cladding panels.
So AVAC takes this concept, integrates those closed PBRs right into the skin,
Yeah.
and it combines a passive job shading with active productive jobs like capturing carbon and making biomass.
It makes the facade productive, not just protective.
Okay, so we have the building's mechanical rhythm and its ability to breathe carbon.
Right.
But every living thing needs water. How does this massive facade deal with urban water scarcity?
This takes us to the third strand of research on biomimetic adaptive facades. The context here is huge. By 2050, 70% of the global population will be urban. We can't afford to have building surfaces that just ignore the water cycle.
And what's so cool here is the design inspiration. It's not from human engineering. It's from nature's cleverest survivors.
That is the soul of biomimicry. They looked at things like the shell of the Namib desert beetle.
Right, the one that pulls water out of the air.
Exactly. It uses these tiny bumps on its ridged shell to condense atmospheric fog directly into droplets it can drink. Or they looked at cactus spines and how their microtextures channel every last bit of rain or fog.
That's such a great visual. So instead of just shunting rainwater into the storm drains, the building is designed to gently drink moisture right out of the air.
That's the goal, to integrate adaptive surfaces that collect this water and bring it back into the local water cycle.
So how does AVAC actually do this? Does the facade start to look like a giant beetle shell?
Hey, not literally, but functionally, yes. The AVAC cladding uses biomimetic microtextures and special hydrophilic coatings.
Materials that love water.
Right. They're designed to attract and hold water fog droplets, rainwater, atmospheric moisture. This collected water is then channeled straight into the vascular network to feed the algae.
That sounds incredible. What about pollution? You're in a city. Aren't you just feeding the algae a cocktail of dust and soot?
That is a critical design hurdle, absolutely. Because the PBRs are closed, they are very sensitive. So the AVAC design has to incorporate a primary filtration stage.
So it's its own little water treatment plant.
A very smart, very localized one, yes. It's built right into the cladding system to ensure the water feeding the algae is clean enough for the biology to thrive.
So you're feeding the system with atmospheric water, captured by the architecture, powered by the wind, and cleaned by integrated filtration. That's closing 3 different resource loops at once.
And when you connect all these dots, the 3 foundations, the kinetic energy, the PBRs, the biomimicry, they synthesize into AVAC's theoretical engine.
It's a totally different way of thinking about a facade.
It's a complete conceptual shift. You stop seeing it as a static barrier and start seeing it as a metabolic, semi-permeable membrane.
Like skin or a leaf. A membrane where energy, matter, and information are constantly crossing boundaries.
And AVAC's unique synergy, the real magic, is that coupling we talked about at the start. The kinetic energy from the wind doesn't just make a trickle of electricity.
It mechanically drives the pump.
It drives the peristaltic pumping action in the vascular network.
Can you break down what peristaltic action means for us?
Sure. Just think about squeezing toothpaste out of a tube. You create a wave of pressure that pushes the contents forward.
Okay.
In AVAC, the wind-actuated components physically squeeze the flexible circulation tubes in that same rhythmic wave-like pattern.
This is so important because it means you barely need any external grid-powered motors for the bulk circulation.
Making it a true zero-energy carbon scrubber. What about those vascular networks themselves? What are they made of?
They're flexible polymer tubes, but with these tiny, highly efficient one-way valves built in. They're designed to mimic plant xylem and phloem.
The internal plumbing of a plant.
Right. They distribute the algal slurry and nutrients, but they also have a second job. They dissipate metabolic heat. They are the algae's life support system.
And since it's a living system, it can't just run on autopilot. It needs adaptive controls. This loops back to the sensors from that first study. It absolutely does. The system has to be adaptive. You need feedback loops. You use optical sensors to track the density of the algae. Other sensors track vibration, temperature, CO2 levels inside the building.
And what does all that data let the system do?
It lets the system's brain, a small microcontroller, dynamically modulate the flow rates. So, for instance, if the sun is just blasting the facade in the afternoon, the controller can increase the algal density by slowing the circulation. This makes the facade darker, which increases the shading effect and prevents overheating both inside the building and in the PBRs.
It's a self-regulating thermal shield.
Exactly.
You know, what really stands out here, maybe more than any single piece of tech, is how absolutely necessary interdisciplinary collaboration is.
It's non-negotiable. The research papers all stress this. You need structural engineers for the wind loads, biologists for the algae, architects to integrate the whole thing beautifully. They all have to be in the same room from day one.
Okay, let's get into the blueprint. The physical structure of this living skin. How exactly does that wind vibration translate into fluid flow? Can you help us visualize the pump?
Yeah, the actuation is really ingenious. The piezoelectric reeds, these flexible plates in the panel frame, their mechanical wobble is used to move a tiny, localized pump chamber. Think of a little asymmetrical rotating piece, a cam, attached to the vibrating reed.
So as the reed wiggles back and forth, it physically spins that cam.
Correct. And a flexible circulation tube is routed right around the edge of that cam. As it spins, it alternately squeezes and releases the tube,
Creating that little pressure wave?
That's the peristaltic wave. It pushes the slurry forward through the valves. The flow rate is then directly proportional to how fast the wind is making that reed vibrate. The wind is literally controlling the building's metabolism.
That is so elegant. But what about the heat? If the facade is soaking up solar energy and the algae are generating their own metabolic heat, how does it help regulate the building's temperature?
This is where that vascular network serves a dual purpose. It's a huge thermal mass. In the summer, the circulating fluid absorbs heat from the building, actively cooling it.
So the building is sweating, in a way.
A bit like that, yes. It's pumping fluid around to maintain a stable internal temperature, just like our blood. And in the winter, you can do the reverse. Waste heat from inside the building can be used to keep the algae at their optimal growth temperature. It integrates directly with the HVAC system.
And the final piece is the harvesting. How do you get the biomass out without shutting the whole thing down?
The excess biomass is extracted periodically through a central manifold. It's usually a highly concentrated slurry. And that harvested material is what closes the loop for the circular bioeconomy.
You process it into biofertilizers, biofuels.
Or even biodegradable bioplastics. So the building isn't just cleaning the air, it's producing the raw materials for manufacturing.
Let's talk numbers. What kind of quantifiable impact are we looking at here? What are the aha moments for you?
The dynamic simulations are pretty compelling, especially on the HVAC side. The models suggest a potential 20% reduction in electricity use for air conditioning.
20%. Just from the facade acting like a smart, living sunbreaker?
And that's before you even get to the carbon sequestration. The potential there is vast. Each square meter of an AVAC facade could sequester between, say, 85 and 770 kilograms of CO2 per year.
Wow, that's a huge range. Why such a big gap?
The lower end reflects a more conservative model, think challenging urban conditions, lower light. The high end reflects an optimal high-intensity setup with very fast-growing algae strains.
But even the low end is a massive contribution.
It's a game changer for neutralizing the building's own carbon footprint.
This really forces us to redefine what architecture even is, doesn't it?
Yeah.
It's not just a structure anymore. It's a living biological system. And that brings up some complex governance hurdles.
Absolutely. For implementation, you need new regulatory frameworks. You need standards for biohybrid facades to ensure public safety, biosafety.
Meaning you don't want the algae getting out.
Exactly. And you need to guarantee structural integrity over decades. But beyond the technical, there's the equity issue.
Right. This can't just become an eco-luxury for fancy new corporate headquarters.
That risk is very real. If AVAC only goes on expensive properties, then lower income areas, which often suffer most from poor air quality and urban heat, they'll miss out completely.
You need policies to prevent that.
You need things like subsidies, green bonds, maybe even community ownership models to ensure this tech gets to affordable housing projects where it can make the biggest difference.
So to wrap this up, the big paradigm shift here is that AVAC allows our cities to move from being passive energy consumers
to becoming active, regenerative systems that manage energy, carbon, and water locally, all powered by the building's own rhythm. It's a pathway toward climate-resilient cities by fundamentally integrating life into our buildings.
And when you transform a building into a complex, self-regulating biological system with a lifespan of decades, it forces you to think about stewardship. And that brings us to a final governance question we want to leave with you. If a facade is actively generating local revenue from selling biomass, from carbon credits, and it's managing public resources like air and water quality, who ultimately owns the benefits? And who bears the long-term responsibility for the health of that living system?
Is it the private building owner? The city?
Or the community that breathes the cleaner air?
A critical question.
Food for thought on the metabolic building of the future. That's all the time we have for this deep dive into aerovascular algae cladding.